Now we will move actually to the last hour. Thank you for everyone for attending and waiting, especially the folks here in the UAE. I know it's Thursday night, right before the weekend. We will try to make it fast. We have the last session is basically we will be covering the cryptographic activities in the here in the UAE. So Professor Abe from Khalifa University will go first, discussing a few of the crypto research in the UAE, especially the projects that we are doing in collaboration between TII and Khalifa University. And after that, I will end up by giving an overview about the different crypto activities that are happening in the Crypto Center and the Technology Innovation Institute. Professor Abe, go ahead, please. Go ahead.
Okay, thank you very much. And again, I'd like to thank you, Dr. Najwa, for giving me the opportunity to talk about cryptographic research at Khalifa University. I'd like also to thank you and thank all the organizers for a really wonderful workshop. I've been thoroughly enjoying it, since yesterday. We've had really a wonderful series of talks and presentations, really high quality. Thank you very much for putting the time to organizing all this. So as Dr. Najwa mentioned, I'm going to cover some of the crypto research that we are doing at Khalifa University. I'd like to acknowledge my colleagues, Dr. Chan Yun and Dr. Shufan, who contributed to this presentation by sharing their own slides about their own projects. So the goal of this presentation is to first, highlight three projects that we are currently working on in the area of information security. All these projects were kicked off in October of last year. Actually, it should be 2020, not 2021, with support from TII Cryptography. The other goal is really to complement the presentations that we had from our colleagues at NYU Abu Dhabi. We had four presentations, 2 yesterday and 2 today. Also, they covered really lots of nice work that's happening here in the UAE in this area. Of course, I'm not going to claim that what I'm going to cover is all the crypto research that's happening at Khalifa University. I'd like to point out that Khalifa University has its own Center for Information Security, in which a fair amount of crypto research is happening and information security research is happening. We have actually our own master's program in this area that's actually open to only UAE nationals. And then we have the EBTIC Center. This is the Ittisalat British Telecom Innovation Center. It's actually more than 10 years old. And within that center, there is also some crypto research that's ongoing. I'm going to present 3 projects. They are all under the one theme, which is fundamental security services. The first one is broadcast authentication for the IoT networks. The second is on secure UAV or drone operations, and then the third one is on secure cloud FPGA. And I'd like to give a warning, which is that I'm not going to share any hard results because this is just starting. But I hope that come next year's seminar, the crypto seminar, we'll have lots to say about our progress in all these projects. So this is the very first one on broadcast authentication in an IoT world. The title of this project is Enhanced MicroTesla Protocol for IoT Environment. This is led by Dr. Chan Yun. And the project here, of course, I'd like to thank Professor Jha for giving such a wonderful survey and also lots of original work on IoT and including some of the security aspects of IoT edge devices. So this research is definitely within that stream of work on IoT devices. where the objective is, of course, to address some of the cybersecurity challenges, including, for example, IoT device and message authentication, the security of the wireless network, the end-to-end data confidentiality, and then the prevention of denial of service and distributed denial of service attacks. And this project is motivated by some shortcomings that have been identified in a very very well-known algorithm for broadcast authentication called Tesla. And I will share with you what the Tesla acronym is in a short while. But the fact of the matter is that Tesla, as it was proposed about now, maybe 20 years ago, does not satisfy all the cybersecurity requirements, and it has several drawbacks, including, for example, the limited length of the keychain, which would actually allow a reply attack. Also, we've seen some improvements on Tesla since it was published 20 years ago, but these improvements, again, they have some shortcomings, including, for example, lack of continuity in the authentication process, which again, opens a window, for the communication to be attacked. And so, as a project goal, the main goal here is to provide a more secure and flexible, lightweight solution, of course, because Tesla was developed very, very early, before the IoT craze that we had since 2010. And so the need for a lightweight solution for broadcast authentication is definitely there, and it's really the objective of this project to develop such a solution. So more specifically, the project will develop a mutual authentication protocol that's based on a second generation Tesla called MicroTesla. And the MicroTesla that's going to be proposed is going to be lightweight, yet able to protect against denial of service and distributed denial of service attacks. The proposed scheme will combine some further ideas that got developed related to Tesla. One of them is called multi-level MicroTesla, and the other one is INF Tesla for identification-based or authentication-based cybersecurity approach for IoT devices. So here is where I'm going to tell you about where this the word Tesla comes from. It's really not the car. It's not Nikola Tesla. It's timed, efficient, stream, loss tolerant authentication, and proposed in a paper by Periggs and colleagues in 2002. It's based on a symmetric MAC and achieves asymmetric properties through the delay of the key disclosure. Now, one problem with the Tesla protocol as it was proposed is first of all, of course, they were aware of complexity implementations, for the hardware, and therefore, in terms of synchronization, they tried to be flexible on the synchronization to reduce hardware complexity. Perig and colleagues also proposed a second generation Tesla called MicroTesla, where the idea is to think about how to reduce computation power, communication bandwidth. The idea wasn't IoT the way we know it, but they were thinking along the line of how to enable Tesla for a wireless sensor network. Later on, there was some more work on multicast authentication with an attempt to overcome the disadvantages of the original Tesla protocol. There was a new synchronization algorithm that was proposed, and and another development was actually the multi-level MicroTesla, in which there was this idea of having some type of a hierarchical broadcast authentication process where you would have multi-levels, and the higher level would authenticate the lower level, and so on and so forth. Now, there are several problems, as you make things, more flexible, or when you try to solve one problem, another problem would occur. For example, one problem that emerged from multi-level Tesla was the long recovery time in case there is a packet loss, right? And that resulted in a discontinuity in the authentication, which again would provide an opportunity for a denial of service attack. So this is where this project is coming from, and this is a table that's comparing these Tesla and all the subsequent generations, MicroTesla, multi-level MicroTesla, and the infinite Tesla. And if you look at this table, you see that every solution had its own shortcomings. For example, again, taking, let's say, multi-level Tesla, this is the lack of continuity in the authentication process, the extra bandwidth that has to be consumed. Even the original Tesla had a scalability problem, and so it wasn't really compatible with the IoT world, where you expect, a huge flexibility for the scalability of anything that you want to do with your IoT network, so as to allow additional entities or additional devices to join the network, yet you want to authenticate them. So and so this is where, again, the main motivation for this project, it's going to look at all these aspects in a holistic way and try to develop a solution that's going to be lightweight, very important. In fact, ultra lightweight for IoT devices, yet that's going to be immune to these denial of service and distributed denial of service attacks. I have highlighted a few things in the tasks and deliverables of this project, the new Tesla protocol for providing lightweight security in IoT devices and wireless sensor networks, ensuring the continuity as this was identified as a problem in multi-level authentication. So ensuring the continuity of mutual authentication and avoiding high demand for memory resources in long key chains. For example, if you are doing multi-level and you have a long chain to manage in your keys, then of course you are adding demands on your memory, and therefore you need to manage that correctly. So this is again one of the aspects that will be addressed by this project. And then I also highlighted in work package 3 the idea of doing first a simulation of the enhanced protocol, and possibly also an implementation. Okay, so that's the first project, and here I have the references, including some of these seminal papers on the Tesla and some of the follow-up papers for improving on Tesla, like MicroTesla, multi-level Tesla, infinite Tesla, and also some of the work that Dr. Yoon has started in collaboration with Professor Damiani on a new 2-level MicroTesla, which was actually a motivation for this line of work. So now I'm going to describe the second project, which is related to secure UAV operation. And the main objective with this project is to provide UAV operation security and develop a service chip that's going to implement the security and crypto protocols for UAV operation. This is a project that's led by Dr. Abdul Hadi Shufan. And in fact, Professor Jha in his presentation mentioned drones quickly in his at the beginning of his presentation, and that's definitely one main area of application of IoT. The drones are considered assets by governments, organizations. Yet, they are assets and at risk. And if you look at the risk landscape for drones, one crazy idea is that you can actually be the victim of a predator drone, that will come and just kill you. That's a possibility. There is also in the threat landscape the presence of an adversary that could be either spoofing on your signals or just jamming your signals and preventing you from communication, including possibly jamming your GPS and causing navigation errors for this drone. There are also in the threat landscape threats that could be actually at the hardware level, presenting themselves as hardware trojans in the very hardware that you are using to operate the drone, or even in the drone itself to make it run. So that's a pretty complex landscape for drones. Okay, and this will motivate having to think very carefully about the threat landscape and then develop security solutions for a drone operation. So the goals of this project is the holistic security analysis, the specification of security objectives and functions, and then the development of a system on chip that will be carried on the drone hardware that would implement some of the countermeasures that are needed to protect the drone operation against these threats. And so, if you look at the drone itself, there are several things that you have to take into account for the development of such SOC. Of course, the drone will have its navigation sensors, the initial motion units, the GPS. It will have application sensors. Every drone is used for some specific application. It could be weather monitoring, it could be surveillance. And so depending on the specific application and the portfolio of flight and application sensors that the drone have, you have to analyze what could be what's at risk, from a security point of view. And then when you want to implement security solutions, you want to, of course, like Dr. Jha very eloquently, described, you need to look at performance, you need to look at power, and all this will, of course, impact drone operation. And so in this project, a holistic view will be taken on all these aspects, and things related to the cost, the size, and the weight of anything that needs to be added for ensuring secure drone operation will be analyzed. But yet, the main objective here is really the SOC, and we will say a few things about it in a short while. So what's the overall approach? The overall approach, the threat landscape, we described some of it. There will be some proposed security protocols. There will be a security and safety verification, performance verification, and this could be done in a modeling and simulation mode. And then there will be an FPGA implementation and embedding the FPGA on the drone, and conduct some experimental validation tests for the whole security solution. Okay. Now, the quantum technology that you see here in the center of the slide is related to key generation, and that's going to be part of the security solution that will be implemented. Of course, the most important case when we want to target, let's say, an experimental setup to illustrate all these security solutions is to use is to use a case scenario for illustrating, the security solution and the impact that might have on security application. What you see here is actually a map of a very important highway. This is really the highway that connects Dubai to Abu Dhabi, the two major cities, in the United Arab Emirates. And along actually this highway, close to this highway, we have the Abu Dhabi International Airport. And of course, this is a very important, very important installation that whose security is extremely crucial. And so flying drones in that neighborhood is going to be uh, uh, an important consideration, of course, from a security and safety viewpoint, whether it's a friendly drone or a non-friendly drone. So that might be actually, this area could be actually, since it's quite open, right? And especially in the neighborhood of the airport, it could be possibly, considered as a nice place to actually doing some experiments, some security experiments on drone operation. So, of course, to make that experiment successful, you have to make your assumptions very, very explicit. The very first thing that we have to identify, of course, is whether we are going to assume that the experiment we are going to deal with is going to be on a friendly drone or an adversary. Okay, and in this case, it's going to be our own drone on which we are going to put our own SOC. So it's going to be a friendly drone. The other thing is it going to be a peer-to-peer type of a transaction for security management, or it's going to be a unified threat management scenario, and then the answer is going to be a unified threat management scenario in which the drone, the operator, or both of them could have access to continuously to the ICT infrastructure, so that threats can be dealt with in a consistent or universal or unified manner. And then, last but not least, do we want to consider multiple drones flying together in a formation, or is it a single drone? And the answer here is that for this assumption, or for this analysis, going to be a single drone. Um, other consideration is the mode selection. Is it going to be autonomous? Fly and forget, or is it going to be controlled? All these are going to be subject to further analysis as part of this project. Is it going to be line of sight or beyond the visual line of sight? Okay, that's another consideration. What type of data we are going to have from the ground? Is it going to be just control, or are we going to communicate between the drone and the ground in channels that are actually not the command and control channels? And then what's going to happen to the data collected from the drone? Is it going to be stored on board, communicated, or both? So many considerations, for us to be able to have a successful experiment. So we identified the selection mode, now the security function selection. What are the security policies? What are the protocols within these policies? And of course, which algorithms we are going to use in every single protocol. So this is all part of this project. Now, when we come to hardware implementation, as we said, the ultimate result is to design an SOC. And of course, you need a vehicle, you need a drone. So what drone are we going to select? And there are several options. And which SOC we are going to use, what platform we are going to do for the SOC. Is it going to be FPGA? Are we going to use a microcontroller, in which we are going to actually program whatever algorithms or whatever protocols we are going to come up with, what's going to be the balance between the hardware and the software in such an implementation, and so many considerations that one has to go through for both, you know, the drone and the SoC platform. And then, you know, as I said, you know, there will be a quantum chip that's going to be responsible for the entropy generation as an entropy source for key generation. And so we need to again, you know, look at the specs. What entropy level do we need? You know, what type of interface is going to have compliance certification? That's going to be all part of this project. Okay, so if you look at all these options, you see that we have a huge design space to explore, and of course the metaphor here is that you know it's not going to compute in light years, hopefully, but you know the design space is quite large. So use case selection, as I mentioned, here you see a summary of all the considerations that I went through for this project: the assumptions, the case selection, the modes of operation, the security functions, and then the technology selections. And of course, all this is going to be based on some threat landscape analysis for the particular drone that we are going to select, along with the a portfolio of applications and sensors that it's going to have. So, again, we just started. Dr. Hadi is leading this project, and he just started. And these are the tasks that he's going to work on over the next 2 to 3 years. And again, you know, these tasks intersect with many of the topics that we had in this seminar, including cryptographic accelerations. Dr. Jha mentioned the importance of doing classification. That's when you want to do, for example, threat identification. So you might need an onboard classifier for identifying your threat. And as part of this project, you know, having onboard classification will be important, with all the consequences that this will entail in terms of performance, you know, accuracy, power consumption, and so on and so forth. Okay, so now I come to the third project, and this third project is entitled Secure FPGA as a Cloud Microservice. I'm leading this project, and the goal here is to work on improving the state of the art in the area of secure cloud computing by exploring the use of FPGAs as a hardware root of trust and as a tamper-resistant root of trust service manager that will provide hardware level access to crypto modules, keys, IO pins, and other resources without the mediation of software. Okay, so the idea here is really to reduce the exposure surface on our cloud resources, hardware cloud resources, and using, you know, the FPGA as the mean for doing such a reduction by eliminating as much as possible the need for writing programs that can provide entry points for attacks on our hardware resources. Now, for the people, I already mentioned FPGA when I talked about the platform options for Dr. Hadi's project. And for the people who are not familiar with this word, you know, FPGA stands for Field Programmable Gate Array. This is basically a silicon device that's programmable at the bare metal level. Okay, it's a device that's not going to be mediated by any software. When you dump your program on it, that program is going to turn some switches on that are implemented by transistors and make connections between components. And these connections are actually copper wires that are running right on the chip. So it's a programmable at the bare metal level. and so it's a good candidate to be a root of trust. And just to maybe illustrate this root of trust idea, the hardware root of trust, I picked up this image from Rambus, a well-known memory company, and they have this picture of an attachment to the CPU that's acting like a hardware root of trust. It's designed in ASIC, and it provides actually services to managing some crypto functions, such as a private memory, such as crypto accelerators for various crypto and encryption and hashing algorithms. So one possible approach, or one possible uh, 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 line of work that we can do is really to forget about using a specific chip for doing this, and using a configurable or a programmable chip such as the FPGA for implementing such a service. So that's one possible motivation. Now the FPGA themselves, have become quite complex, and the FPGA vendors are very much aware of the security challenges to their FPGA devices. And so they have started, of course, implementing security functions within the FPGA devices that are providing. So it's programmable, yet it comes with some. You can consider these as libraries, right? That you can use directly to enhance the security of your programmable logic. Okay, so you will be basically doing your logic at the bottom here. That's as a designer, you'll be designing with what you have at the bottom, but you will be also using what's made available to you by the vendor for enhancing any system, not just the crypto, but it could be your memory blocks. It could be if you need, for example, support from special IPs, such as a microcontroller that you need in your design. And so in this example, you see how the vendor has actually provided not just the crypto that's important to us, but also some other functions to the ARM processor, for example, to help with some other design objectives, such as, for example, running a microcontroller in conjunction with the custom design that you are implementing in your FPGA. Okay, so that's the vendors are very much aware of the security aspects, and that's really on the vendor side. Now, on the cloud provider sides, they are also aware of the hardware benefits of the FPGAs, and that's why they started providing FPGA as a cloud service. And here I have an image from the Amazon Web Services from AWS. They have an FPGA acceleration service called the F1 service. And you can actually ask them to provide you with FPGA resources the same way you can ask them to provide you with CPU or GPU resources. And they create an image. So they create an Amazon machine image, and you can create an Amazon machine image that's a CPU. It could be a very high-end CPU with multi-cores, with tons of memory, and so on and so forth. But now you can also, or it's been now 2 years or so, you can create an Amazon FPGA image. They call it an AFI. And in the background, you'll be provided with compute resources that are FPGA based. Of course, there is a methodology for how to use this service, especially in terms of porting, the design that you have on the FPGA resource that's going to be provided by the cloud provider. Now, what about security on the cloud level, right? This is and this is also a very important issue. The cloud providers are aware of it, but unfortunately, not much information is being disclosed by the cloud vendors on FPGA security. But you see here some of the statements that AWS or Amazon has been making, the FPGA image, the Amazon FPGA image, is declared as secured and encrypted, dynamically loaded into the FPGA. So you can think of this AFI image as the software that will include your own design that's going to be burned on the FPGA resources. That's going to be programming, at the bare metal level that we mentioned previously. And so they declare this AFI as being, secured and encrypted, cannot be copied or downloaded. So this is a security layer that they have added, to prevent tampering with these AFI. And you can refer to this. I think it was a tutorial or a presentation uh, by Amazon at Hot Chips conference. This is something that you can access on the web. Now, one thing I want to point out here is that the crux in terms of FPGA security is what we call bitstream security. What's the bitstream? The bitstream is really at the end, once you do the design and you want to burn your program into the FPGA, you generate a binary file. I mean, as a programmer, you can think of it as the object at the end object file that you run, to execute a program, right? So this bitstream is also a binary file that is going to program, your FPGA at the hardware level, and that bitstream could be exposed to attacks. Now, of course, AWS makes the bitstream as part of the AFI, which is itself, secured and encrypted. And once you have your bitstream out, as a developer, you can no longer have access, and so since it's secure now, so the developer authentication is no longer needed. Unfortunately, this whole process is not publicly documented, and so this is in itself is a motivation for what we are doing in this project. We would like to expose all these security aspects of bitstream risks. This is a very recent paper. Actually, it appeared just 2 months ago, it appeared less than 2 years ago, and it shows you the threat landscape now of the bitstream, in an FPGA, in a modern FPGA process, okay, or in a state-of-the-art FPGA process, and you see that at every level of bitstream life, you have a number of risks, a number of threats that could actually impact the security of your FPGA FPGA service. Okay, so it could be at the bitstream generation level. Now, don't forget, like, to generate the bitstream, I really have to use computer-aided design code, right? And that computer-aided design code, it could also involve some of the IP that I talked about, right? I showed you a modern FPGA that has lots of IP, and you can bring also third-party IP. So you could actually you could be running risks just at the level where you are generating your bitstream, and so you really need to be careful at that level. And throughout the life, you can have risks, fault injections, tampering, happening throughout the life of the bitstream. And so you see the exposure is quite big. And just saying that, okay, we took your bitstream, we put it in a secure, encrypted, and that's it. You really cannot touch it. May not be sufficient, and we really need to expose that so that we can develop some security solutions. So one possible security solution for protecting the bitstream is an idea that's been quite well researched in the hardware security area, which is the idea of logic locking. And I'd like to recognize our colleagues from New York University, Abu Dhabi, because they have contributed a great deal to this line of research on logic locking. And I have documented here a paper from the NYUAD team that was published, I think it was the Computer and Communication Security Conference 2017. Now, originally, logic locking actually was developed to protect silicon hardware against attacks such as intellectual property piracy, counterfeiting of silicon hardware trojans, reverse engineering, or overbuilding attacks. Okay, and the idea of logic locking is really to augment the logic of your design with additional circuits that will operate only with keys that you and the legitimate user of your hardware will know. Okay, so that's the fundamental idea. And of course, this was developed specifically to deal with security threats that could happen throughout the life of a design and throughout the cycle. You know, from design to fabrication to packaging and then to usage. We are now taking this idea and trying to bring it to the FPGA world to improve FPGA bitstream security and use the programmability of the FPGA to actually revisit many of the ideas that were researched maybe in the ASIC world or in the chip design world, but do them in a reconfigurable world. So we have this idea of developing a programmable root of trust using FPGA. So this would be unlike what Rambus had, where they had just a fixed chip. That's a root of trust. And if you are the user, or if you are the provider of this root of trust service, and you have the FPGA available to you, then maybe there are things that you can do programmatically and improve your root of trust service. Programmable hardware security. So logic locking, once you pick up your logic locking method, and there are many of them, it's fixed in the hardware. Yet, when in an FPGA world, the programmability might give you some flexibility on actually changing that logic locking design, or doing multiple logic locking designs with multiple keys, and improving, even further bitstream security. Programmability will allow us also to think about post-quantum cryptographic services. Another thing that is now very important in the FPGA world is the exposure of FPGAs to side channel attacks. And this is a mixed blessing, right? The FPGA is a mixed blessing. There could be some more exposure to side channel attacks, but the programmability might actually allow us to develop countermeasures and also to adapt these countermeasures in a programmable way to emerging attacks. Now, a little bit like the drone example or the UAV security example, we do have a case in mind, and the case study in mind, or the usage mode in mind that we have is to develop is to work on an AI modeling and a secure AI modeling service that's going to be provided through a secure FPGA. Now, I'd like to mention that in this project, we will focus more on the hardware level of things. We are leveraging, for the cloud aspects, we are leveraging another project of ours that's dedicated to developing microservice architectures and efficiency models for cloud computing services. Such a microservice architecture, we hope to take it almost as is, and use it in the secure FPGA context. Now, this cloud microservice includes important aspects of the cloud computing, such as service level agreements, We call them now microservice level agreements, and also quality of service. And now we call it quality of microservice. Again, microservicing is one of these emerging trends in cloud computing. Um, uh, it's a very active area in cloud computing, in which we are seeing, software tools, open source, are being developed, and we are piggybacking on this activity, for this for the cloud aspect of this project. This is our own implementation of the microservice. We have software that we are using, and we are going to piggyback on that software again for the cloud aspects. The security aspect will happen as part of this project, the Secure FPGA. Okay, so this is the task list. It's identical to threats that I mentioned to you. And I'm going to maybe stop here, Dr. Najwa. Maybe I took more than my allocated time.
That's not a problem.
And just to summarize then, I have presented 3 ongoing projects that are supported by TII Crypto under the common theme of fundamental security services. There was a broadcast authentication for IoT, the secure UAV operation, and the secure FPGA as a cloud service. And if you think about these projects, you see that they are actually spanning, the whole landscape. One of them is for authentication. The other one is for secure operation. And then the third one is really for cloud computing. And so that right there, you have a really nice portfolio of projects spanning security aspects of cloud and IoT computing. Thank you very much. And if there is time, I'll be more than happy to take a few questions. Thank you very much.
Thank you very much, Professor Abe. We appreciate you stayed late with us.
No problem. Anytime.
Thank you very much. Thank you, Professor Abe. Thank you for all our speakers and keynote speakers today.